the pattern we established with single samples and with confidence intervals was that we would first study means and means from a normal population, and then we said, well, we don't know certain parameters, and that led us to the t-distribution. And then when we started looking at variances, we got into the chi-squared distribution. Same thing's going to happen here as we start thinking about hypothesis tests for variances. Now, big key question in real practice is that we end up trying to seek ways that we can reduce variability. That's the bane of our world, is either we have man-made induced variability or we have natural inherent variability, and when we're producing things, we'd like to try to reduce that variability. We come up with different approaches, and we like to know which approach is statistically more valid, statistically producing a better quality result. And so that leads us to this question of hypothesis testing for ratios of variance. Why the ratio, you'll see in just a second. A couple of key things here as we develop this work, and that is that we're coming out of two normal populations. That's crucial in the validity of the work. And in terms of our notation, we're dealing with two sample sets, x1, x2, where they have size of n1 and n2. And although they don't have to be equal to each other, some of the tables, curves, that we're going to use, particularly the operating characteristic curves, rely on those two being the same. The tables that we use, actually, those two won't be in general, and it'll be very important to keep track of which is which is sitting in the numerator and which is sitting in the denominator of our ratio. Okay? We have, of course, along with two sample sets, two sample variances, calculated in our normal way with the n-1. And a typical hypothesis test will have a null hypothesis where we set the variances equal to each other. And because of that, then the form of our test statistic will turn out to be associated with this f. And you can imagine from our work with the t-distribution that probably means that we have an f distribution, and that turns out to be the case. And it's just a ratio of the two sample variances. Right? Now, the background that leads to this is that f, when it's the ratio of the sample variance to its own population variance, and then likewise in the denominator, the second population, is that particular form has as a sampling distribution an f distribution. Now, this is kind of unfortunate terminology, because in probability we use capital F to mean the CDF and lowercase f to mean the PDF, and you're going to have to keep track of the two different worlds here because they do collide a little bit. Right? Another very crucial aspect here, that the F distribution has n-1 degrees of freedom from the numerator, and it has n2 minus 1 degrees of freedom from the denominator, and we're going to keep those separate. We do not combine those. It's crucial to keep those separate, and it's crucial to keep track of which is which, and to be very careful how you read off table values, and how you take reciprocals will be important. A key element in the background is that if you go back to to our work previously, the combination of our sample variance to our population variance multiplied by n minus 1 had a chi-squared distribution. That was a fundamental aspect that we worked with previously. Likewise, then obviously that was true also of the second population. Now, part of that, and key to our work here, is that the two populations are independent of each other, and they're coming from a normal population. We need both of these to get us to the F distribution. Right, now, one more thing before we head off into the numerical example, and that is that the shape of the F distribution is similar to the chi-squared, but it actually ends up with more flexibility because we have now multiple parameters. We've got the n minus 1 degrees of freedom, we'll call that U, and n minus 2, or n2 minus 1 is going to be the V degrees of freedom. That's important to, again, to keep those very clear and distinct for the reasons that you're going to see on this particular plot of the PDF of F. Right, now this is where I really don't like the symbols, but it is what it is. We'll let x be our independent variable here, and this F is the PDF, not anything associated with this stuff going on here directly, right, in terms of just symbols. Right, so this lowercase f means the PDF. And that shape, again, looks similar to the chi-squared, and as I draw it qualitatively, you couldn't tell the difference between the two. Here's where the symbols really get kind of nasty. If this little tail area is alpha, then we call this x value also little f, right? These are not the same things right here, and that's kind of goofy and confusing. F sub alpha, and then it's got 2 degrees of freedom, u and v. The order is important. This is f sub alpha u v, and then down here in that region we end up with the F. I keep looking this up every time myself, even though I know this and I'm confident of it. I keep looking it up to make sure I don't make a mistake, because one little mistake really gets us here. Right, so this is 1 minus alpha u comma v. Now this looks a little goofy here, 1 minus alpha versus alpha. That looks a little strange. But here's the really weird kicker, that f sub 1 minus alpha u v is equal to the reciprocal of f sub alpha v u. Oh goodness, I'm below the screen. So I'll repeat that. F sub 1 minus alpha u v is equal to 1 over f alpha v u. We've switched the order of the subscripts here, the v and the u. V is the denominator and u is the numerator in this case. Right? And that's crucial when you pull out the table values. You'll see that here in just a second in the numerical example.